everyone. This is Hassan Younes. I'm the co-CEO of grfn. We're a consultancy based off the UAE. We also have offices in Cairo, and we do a lot of work on buildings when it comes to MEP design. We look also into sustainability, energy modeling, energy auditing, commissioning, retrofit projects, indoor air quality, which is the topic of today. So I'm going to start with the presentation. This is a presentation on ASHRAE standard 62.1, which is the standard that we use in the UAE when it comes to requirements of ventilation and indoor air quality. So here's the outline for today's presentation. We're going to look at an overview of the standard 62.1. That will take a good chunk of our time for this presentation. Then we'll look into demand control ventilation, some defects that we find in outdoor air systems in designs and installations. Then we're going to talk about energy recovery systems, the requirements of 90.1, and then we go into questions. So what is standard 62.1? The purpose of the standard is to specify minimum ventilation rates and other measures intended to provide indoor air quality that is acceptable to human occupants and that minimizes adverse health effects. That's basically the standard's purpose. If you look at the document, that is exactly what it says there. So why this was created? It was created mainly to look into indoor air quality. It has been a requirement for many other codes like NFPA 5000, rating systems like LEED, Istidama in Abu Dhabi, International Mechanical Code in around the world, I would say. Dubai Green Building Regulations in SAFAT also lists this standard as one of the requirements. Some history of the standard. In 1973, it was first issued. And if you look at the requirements back then, in terms of quantity of outside air per person, was 15 CFM. That was in 1973. Once we had the energy issue in the US with the oil embargo, they thought of ways to reduce energy consumption, and they said, well, why don't we just reduce the outdoor air ventilation? That will reduce the consumption of our fans and our cooling and heating systems. And they went drastically from 15 to 5, which was a bit of a, I would say, too low. And then they found out that their buildings were having the sick building syndrome, and occupants are not feeling very well because of that. So these lower ventilations had adverse health effects on the occupants, especially in office buildings. So then they decided to increase those rates again because of the sick building syndrome, and 1989 had higher rates. Little change was in 1999. 2001, the main change was that the standard was written more in mandatory language so that states or different jurisdictions can use that standard and change it into code in a much easier way. No need to change a lot of the wording. 2004 was a key change, especially in the ventilation rate procedure, where now we need to look into not just the number of people, but also the area. Because the idea behind it was that furniture, paint do produce some pollutants that we need to take care of, and not just humans producing those pollutants. In 2007, many addenda was added. Then we had 2013, 16, and now we have the 2019 version. But in terms of the quantity per person as a general, let's say, comparison, it kind of went back to 1973 in terms of quantity. So it's almost 17 CFM per person when taking into account the area that is occupied by one person in an office building, which is normally taken as one person per 20 square meter. That's just a representation of what we just talked about. Now, what were the major changes in 2004? There was no thermal comfort requirements in the standard, and Basically, if you want to look into thermal comfort, you need to refer to ASHRAE standard 55. Minimum ventilation rate table were revised, and now they apply only to non-smoking spaces. And there was a new calculation procedure that we're going to have a look at. And there was an upper relative humidity that was set to 65%, so that no bacteria or let's say mold can thrive. We need to keep the relative humidity below 65%. So the sections of the standard, most of the ASHRAE standards, they start with the purpose, scope, definitions, and then it goes into the main body of the standard, the requirements. So in this case, outdoor air quality, then systems and equipment. Then it goes into procedures, which is kind of the main part that normally like consultants would look at, especially the ventilation rate procedure. Then there's a section on construction system startup, operation and maintenance, and then some references. But in general, you would need to look at all the sections to be able to comply with the standard. You can't just look at section 6 and say, I am complying with the standard because I'm delivering the quantities as per the table 6. In terms of the requirement of outside air per person or per area. You need to look at all the different sections and check the requirements and apply them. Section 5, systems and equipment highlights. It talks about mechanical ventilation system controls, the outdoor air intakes, particulate matter removal, relative humidity and exfiltration, and also a bit on energy recovery. In terms of controls, it says that systems shall include controls, manual or automatic, that enable the outside air fan system to operate whenever the space is occupied and to maintain the minimum flow required by Section 6. So it just basically tells you that whenever there are people inside the building, the ventilation system should be turned on. If there's no people in the building, excuse me, then there's no issue. You can turn off the system, but whenever there's even one person in the building, you need to turn on that system so that basically they have good indoor air quality. Outdoor air intakes, it's basically the separation distance that's required between the air intakes and any pollutant sources. And these pollutant sources could be exhaust from the building. So as you can see here in this illustration that I've actually drew with one of the drafting team members in maybe 2010, I believe. You can see that there are different pollutant sources. The road could be one, garbage, cooling towers, exhaust, kitchen exhaust, lab exhaust. And there's a minimum distance that you need to separate the outdoor air intakes from that so that no contamination can be recirculated back to your building. Or if you have any other sources of contamination like the road or garbage cans, then you need to separate and have a minimum distance between the intake and those pollutant sources. Another important point is the particulate matter removal. The standard does require that you need to have a filter or air cleaner, basically, that should have an MERV of 8 when tested as per ASHRAE standard 52.2. So if you have a coil that might have condensation, so probably any coil in the UAE will have condensation, then you'd need to have a filter. If that coil will not have any condensation, so if you're in a very dry climate, maybe, then you might not need to put this filter. But in general, it is required because most of the coils will get wet. MERV 8 is the requirement in the 2016 version. Before that, it was MERV 6. So that mainly will introduce a little bit of higher pressure drop on your fan. So you might need to increase the fan capacity in terms of static pressure. That might increase the cost or the running cost of that fan, but it's important to have this high efficiency filter to capture contaminants. Relative humidity, 65% was the norm. In 2019, that has been changed to 15 degrees C dew points. As you can see here on the screen, the 65% basically is that highlighted in red. Anything below it is fine, anything above it is not. So whatever is in red or above the red is not okay as per the standard. But in 2019, that has been kind of upgraded, I would say. And now you cannot go beyond 15 degrees C dew points. You can see that line that represents the 15 degrees C dew point. Anywhere below that line, you're fine and compliant with the standard. Anywhere on the psychrometric chart above that line, you're not compliant with the standard. So that should happen during occupied and unoccupied hours, because you don't want the mold to thrive during even non-occupied hours. So any point in time, the dew point should be below 15 degrees C. Additionally, the building should be positively pressurized if you have any dehumidification happening. So if you have any condensation happening on the coils, the building should be positively pressurized. You don't want to have humid outside air to go inside the building and cause condensation and high humidity levels. Energy recovery, this is basically acknowledging the fact that energy recovery devices will have some cross-contamination between the exhaust and the outside air. And here it says that if the heat recovery is happening between exhaust air of class 2, so class 2 air is basically something coming out of a pantry or a toilet. Class 3 air, maybe air coming out of trash room. So class 1 is like the best class, which has the lowest amount of pollutants and contaminants, whereas like class 2, 3, and 4 become more and more loaded with pollutants, class 4 being the worst, and laboratory exhaust, lab exhaust would be one of them. So if you have, let's say, class 2 exhaust, then you can, 10% of that can go into the outside air, the fresh air, and that is fine as per the standard. If it's class 3, then 5% is the maximum that can be transferred. And again, it should be non-intentional transfer, so it's cross-contamination happening, because these wheels or these energy recovery devices do have cross-contamination. You cannot use class 4 air for heat recovery, because you're not allowed to mix any of that with the outside air. Now, the most important probably section of the standard is the procedures. So we have 3 procedures to comply with the standard: the VRP, or the ventilation rate procedure, the indoor air quality procedure, and the natural ventilation. The VRP is the most widely used. This is what we normally use, let's say, to comply with the requirements from, let's say, the municipalities in the UAE. With Sidama, same thing with LEED. In most cases, we use the VRP. So it's a prescriptive procedure where outdoor air intake rates are determined according to the space type, its area, and its population. So we'd go to that particular sheet in the or table in the standard, look at the, let's say, type of occupancy, let's say an office building, and then we'll see that for an office building, it shows that 5 CFM, or 2.5 liter per second per person, is required, and around 0.3 liter per second per square meter is required for the area. So we check the area, check the number of people, and use that equation to come up with the required outdoor air that needs to reach that zone. Now, the indoor air quality procedure, it's basically looking at contaminants. So you need to figure out what kind of contaminants and pollutants will be emitted in that particular room. And then based on the outdoor concentration of these contaminants, you can do a mass balance equation to come up with the required outside air to be delivered. Now, it's not widely used because it needs more work to be done, and it needs more knowledge about what are the potential contaminants in the building. But it normally does end up with a lower outdoor air rates compared to the ventilation rate procedure. So there might be some savings here, but it's more complex and not widely used. And some jurisdictions do not accept it as a way to comply with the standard. The natural ventilation procedure, if you're in a climate that does allow that, you can use natural ventilation, but it has to be combined with a mechanical ventilation. So it's more of a hybrid ventilation system. Again, it's not very widely used, especially in here because of the climate that we have. So this is why we are focusing mostly on the VRP in this particular presentation. So this is the equation basically that was introduced in 2004. And as you can see, V sub BZ is equal to rate per person times the population, the number of people, plus the rate per area times the area. This is basically can be taken from the tables. And you, based on the type of occupancy, you go to the table and find out these numbers and plug them in and get the required volume of outside air that should reach the breathing zone. Now, once you get to that number, you need to divide by the distribution effectiveness. And that basically depends on the type of distribution systems you have. In general, what you see, let's say, in buildings in the GCC, you'd find cold seating supply in general. So that will give you an effectiveness of 1. So it's the same number that you've calculated in the previous step will remain the same. If you have, let's say, like the space and ventilation, you divide by 1.2, so you actually decrease the amount of required outside air, because the space ventilation method can help in reducing the contaminants by picking them up from the kind of like floor up to the exhaust, and thus you get a better figure and a lower amount of outside air as required. Other, let's say, hot seating supply would result in 0.8 of distribution effectiveness, and that will mean that you need to increase the amount of outside air because of that. So if you are in a hot climate, in your cold climate, and you're supplying hot air that is 8 degrees C more than the space temperature, then you'll end up with extra required outside air, because most of that outside air will be stuck to the seating, because hot air is at lower density, so it will from the buoyancy effect, it will basically, some of it will stick to the seating and will not reach the occupants, and this is why you're penalized and you need to supply more outside air. Now, if you have a dedicated outdoor air system and you are basically supplying through what we call sometimes fresh air handling units to individual zones, then just adding all those zones flows basically will give you the required outside air intake on that fresh air handling unit or outside air handling unit. So as an example, if you have an office building with 100 zones, each zone is 200 square feet or 20 square meters, and each zone has 1 occupant, then each zone would require 17 CFM, or around 8.5 liters per second. If we have 100 zones, you multiply that by 100, and we end up with 1,700 CFM for the whole outdoor air handling unit, which is equal to almost 850 liters per second. So this is how we calculate how much outside air is required for that particular outside air handling unit. Now, for multiple zone systems, if you have an air handling unit that has a outside air, and then you have some return air, and you're supplying, let's say, more than 2 rooms, and then it gets more complicated, and you need to do a little bit more of calculation there. And maybe, if you're interested about that, we at the ASHRAE Global Training Center, I gave a course on 62.1 that covers that part. So if you have air handling units, especially with VAV boxes, then it becomes more complicated. And in that case, you need to, apply, more steps to get to the required air intake value on the outdoor air handling unit, or the air handling unit in this case. Exhaust also is required. So some specific rooms, even if you're doing natural ventilation, you'd need to have mechanical exhaust on these rooms, like toilets, kitchens, and so on and so forth. So normally it's taken from that particular table. Ventilation in smoking areas. The standard does not prescribe ventilation rates for smoking areas, so you won't be able to find, well, for a smoking zone, this is the required outside air per person. It's not part of the standard. It's basically up to you to decide how much outside air. Just says it should be more, but it does not advocate how much. Basically, it's up to the user or the jurisdiction to hint or give the consultants the requirements of how much outside air is required. Now, mind you, now in we are in a pandemic, and since a very long time, ASHRAE was saying that this virus could be airborne, and I think even now the World Health Organization, they can admit that it is. So it's very important to understand that the more ventilation we have in these particular moments when we have a airborne pandemic, the more ventilation we have, the better, and less viral load we'd have in the building, and with that, we'll have less infections. Now, coming to the demand control ventilation, it's normally used to reduce energy consumption when we don't need that amount of ventilation because we have lower occupancy at different points in time. If it's, let's say, an office building and the same number of people are there, demand control ventilation won't help. We can just turn off the machines when people leave the building and then turn them back on when they arrive. But if you have, let's say, a meeting room where people, sometimes it's 20 people in that room, sometimes it's only 2. So this varying load requirement or outside air requirement, we can take advantage of that. And when we have only 2 people, we can just provide the required outside air for these 2 people, plus the area requirement, which remains constant. And in that case, we'd save some energy. Now, it's not recommended to do demand control ventilation during the pandemic, so we prefer to turn that off when we have airborne, let's say, transmission possibility, which is the case with the coronavirus. And it's recommended whenever you have more than 25 people per 1,000 square feet, it's recommended to use DCV, and you have this movement and the number of people is not constant in that particular room. The usual set point is 1,000 ppm, and that's normally for an office building, which it's around 600 ppm above the outdoor concentration. However, if you look at the different occupancy levels or different occupancies, you might end up with, even if you apply the standard 62.1 requirements in terms of amount of outside air, you might end up with a ppm of 1,460 in some of the occupancies. Like if you go to the movies, let's say, and in the cinema. In the cinema, you might have high ppm because you have a lot of people, even if you supply the required outside air. That you should not panic from that. That's completely normal. The 1,000 is mainly for office buildings with an occupancy of 20 or 1 person per 20 square meter. So in general, what we recommend is to look at the steady state concentration levels, and then use 90% of that calculated amount as a set point rather than just using 1,000. Mind you that for offices, it is recommended to go even below 1,000 because some studies have shown that cognitive abilities are better with a low CO2 level. So it depends on the occupancy type. I would suggest for like schools, universities, offices, spaces, go to the lowest possible. Maybe 800 ppm would be the recommended value. But anywhere else, if you don't have a pandemic, you can increase the level of ppm as per the standard requirements. And that should be fine. You shouldn't face any issues in that. This is kind of a schematic showing the outside air handling units that is connected to the different spaces, and you have CO2 sensors that are basically changing the amount of outside air that goes into every space. So we'd have a VAV box maybe connected, and then it will change the amount of outside air based on the CO2 levels. If the CO2 levels go higher than the set point, then the VAV damper will open and more outside air will come into that room. Some of the current defects we see here in the outdoor air systems, over-ventilating and during unoccupied hours, that adds more cooling and ventilation energy. Basically you should just turn them off if there's no one there. No use of energy recovery devices. Under-ventilating, which leads to a sick building syndrome and also higher transmission of viruses. Design conditions used are for cooling and not for dehumidification. And normally you want to use the dehumidification or evaporation design conditions for outside air handling units, especially in hot and humid climates. So as an example, if you look at the cooling conditions for Abu Dhabi at 0.4%, meaning that this condition will be exceeded 35 hours of the year. You can see that the outdoor conditions are 43 degrees C, a dry bulb, and a main coincident wet bulb of 23.9 degrees C. This will result in an enthalpy of 71 kilojoule per kilogram. If you look at the evaporation conditions for Abu Dhabi, you'll find that the dry bulb is 34.6 and the wet bulb is 30.8. Which is like kind of the most humid condition. And you can see that the enthalpy is 122 kilojoule per kilogram, which is much higher than the one used for the highest dry bulb, which is 43 degrees C. So you need to make sure that you're using the right conditions when you're sizing your outside air handling units. In terms of energy recovery, we always recommend to use energy recovery because it does reduce the cooling load drastically. So you might reduce 60% to 70% of the cooling load if you use heat recovery with a single wheel. Maybe reduce 60%. With a double wheel, you might reduce 70% of the cooling load on the outdoor air handling unit. And it will reduce your chiller capacity or district cooling connected load. It will reduce the amount of pumping required. So it has a cascading effect. It might add a little bit of cost on the heat recovery device itself, on the outside air handling unit, but it will reduce the cost of cooling capacity and the associated auxiliaries with that. This is a schematic showing like two wheels. And there's also another wheel for desiccant dehumidification system. So you can see there's one wheel, which is a total enthalpy, and there's a sensible energy recovery just after the cooling coil that will basically do a free reheat for the outside air, so you don't overcool the spaces. At the same time, it will cool down the exhaust further, so you have more and better dehumidification and cooling at the enthalpy wheel. So energy wheels are rotary air-to-air enthalpy exchangers that exchange sensible and latent heat simultaneously between the incoming outside air and the exiting exhaust air. It has a sensible effectiveness and a latent effectiveness, so it means it can cool and dehumidify the air. Normally, there's a type of desiccant on the wheel that can suck out the humidity from one side and then send it to the other side, which is the exhaust. You have other types like plate heat exchangers that also could be used. But normally, in general, we use heat recovery wheels. So the sensible wheel, it normally comes in aluminum, copper, stainless steel, and mono, and it transfers only sensible heat, and the rotation speed is around 20 rounds per minute. Passive desiccant wheel, that's another way to, instead of the heat recovery wheel, you can use the passive desiccant wheel. And in this case, or instead of this sensible heat recovery wheel, you can put the passive dehumidification wheel, and that will further dehumidify the outside air. So if you need or want really dehumidified air, that could be the solution. It's a bit more expensive, and that wheel runs for 20 rounds per hour compared to 20 rounds per minute for the other types of wheels. But it is a good option if you want really high dehumidification or get the outside air to a really low humidity level. This is kind of how it looks like. If we look at the requirements, normally when it comes to energy efficiency for buildings, the go-to standard is ASHRAE 90.1. Obviously, in terms of code, it's the International Energy Conservation Code. So it normally would require heat recovery for certain capacities. In the newest version of 90.1, it would depend on the climate zone. So let's say if you take Dubai as an example, it sits in climate zone 0B, which is extremely hot and dry. They call it dry because there's not a lot of rain. It's basically, this is how they classify dry and wet zones. It depends on the amount of rainfall. It's not about the humidity levels. So based on that, the standard does prescribe like when do you need to have outside air heat recovery. So the 5000 CFM is still in the, let's say, Dubai Green Building codes or regulations. But if you look at the latest 90.1, then it depends on the climate zone. And you can see, let's say for a place like Dubai, if you have a total outdoor air handling unit, the quantity where you need to add a heat recovery are much less than the 5,000 that is specified in this standard. Thank you very much, and be happy to take any questions.
Thank you so much, Hassan, for this insightful presentation. Hello to everyone who has joined us today. This is Manali from the Big Five team. Hope you've enjoyed the presentation. We have some interesting questions which have come in from the audience for you, Hassan. Should we get started?
Sure, thanks, Manali.
What are some important questions to ask while approaching IAQ for a building owner looking at acquiring an existing or new building?
That's a very good question. I always think people renting or buying apartments or buildings, they don't ask the right questions. So if I was acquiring a building, I would want to see what kind of ventilation systems they have. They have a dedicated fresh air handling unit to serve the building, which would be a better case compared to either not having any ventilation system or connecting the outside air to the fan coils in the apartments, which normally would create humidity issues, mold, so on and so forth. So I would look at the ventilation rates, like I can just do some sanity checks of liter per second per square meter or per person for that building to see if it's properly size or not. Do they have heat recovery so that I know the bill is not going to be very high on those units? Look into the exhaust. So they have a dedicated exhaust. Is it connected to the heat recovery section of the fresh air handling unit? These are the main questions. Maybe I'll ask on the filters that they have on their outdoor air handling units if they have one. So these are the main ones you'd want to check. And also if they have any maintenance logs, how are they maintaining those? I would go do a visual check, see what's the condition of the outdoor air handling units.
Okay, thank you. At what point during the building life cycle does one have to consider indoor air quality provisions?
I would say every 5 years. And in the standard ASHRAE 62.1, there is a maintenance section. So it says what are the things that need to be done on a monthly basis, every 6 months and every year. And then every 5 years, you probably would need to rebalance the system, recommission it, make sure everything is okay. So I would say like a major kind of look at the system would be every 5 years.
All right, thank you. And what is the recommended MERV rating for an office space in the Middle East? And what are the main criteria to determine the right MERV rating?
So if we look at the standard as an example for the fan coil units, so any wet coil basically would need an MERV 8. This is as per the latest. Early version of the standard used to be 6. Now, if you're looking at fresh air handling units, anything that's handling outside air, and we know that in the Middle East, in general, we have a lot of dust. So that dust, especially PM10 and PM2.5, and that issue is important to capture and not let it go into the occupied spaces. So an MERV 13 is recommended, maybe a little bit more, depending on which city. So like in Kuwait, maybe MERV 14 or 15 is recommended. There is a very nice ASHRAE article. So if you have access to the ASHRAE articles, there's one that shows like every city, what is the recommended MERV value based on the amount of PM2.5 on the outside. But a 13 value is good enough in general for that purpose.
Okay, thanks. I think we're just going to wait for a few seconds to see if we have any more questions, because this was the last one from the audience so far. All right, I think I just got one. Can a good insulation system replace a good ventilation to conserve it or optimize it?
Good insulation system?
Yes. A good insulation system replace a good ventilation.
I mean, these are two separate topics. Insulation can be used on ducts, on pipes, on building envelope. They're not directly connected. So, no, you need to have both systems. And if you're talking about insulation on the ventilation system, so if anything that's carrying cold air or hot air that is different from the outside air, you need to insulate it properly so you don't have any heat losses or heat gains. Now, coming back to the MERV question, like for the pandemic, the recommendation is to use MERV 14. So if you have any air handling units that's recirculating air within the space, the recommendation is to go for MERV 14.
Okay. What kind of quality checks are done by the regulation bodies to ensure acceptable exhausts coming out of any premise, whether through filtration system or direct?
I think that depends on the authority. So every authority, every jurisdiction, they have their own procedures, but in general, they would act either on complaints. If there is a complaint from that building, they normally would send an inspector to check it out. And in some other jurisdictions, they have specific requirements and specific visits to look into indoor air quality. So it's not a specific one. It really depends on the jurisdiction.
Okay, thank you. What is the best dry temperature or wet temperature to calculate the fresh air in Abu Dhabi, according to you?
So if the question is to calculate the cooling load requirement or the capacity of the cooling coil, then you'd need to look at the evaporation or dehumidification design conditions from ASHRAE. So that would be around, for Abu Dhabi, around 35 or 34.8 degrees C dry bulb and a 30.5 degrees C wet bulb. So you're looking at the worst case humidity condition because that is the one that's having the highest enthalpy, rather than looking at the highest dry bulb, which is normally 46, but it does not give the highest enthalpy. So yeah, 35, 30 almost, or a little bit less than 35, maybe 34.8, 30.5 wet bulb are the temperatures normally that should be used to calculate your fresh air load for a dedicated fresh air handling unit.
Okay. And the last one, is it required to add fresh air to spaces cooled by split high wall units or not?
Yeah, of course. I mean, as per the standard, health and safety, you should not have any occupied space with no ventilation, whether it's natural or whether you open the windows, whether it's mechanical ventilation. You should always have ventilation if you have people inside. If there's no one inside, if it's a store, then it's fine. If people are staying there for more than 15 minutes, then ventilation is a requirement.
All right. I'm sorry, I just said it's last, but I think we just got a few more questions. So do you mind if I just ask you a couple more?
Sure.
Could you summarize some of the high-level periodic maintenance requirements in the standard, especially focusing on the cooling coil?
So if you look at the standard, there are a lot of visual inspections to look at: cleaning the drain pan, cleaning the coil itself, looking at the fan to see if it's working properly, the motor, need to do any lubrication, looking at the filters, cleaning the filters or changing them. You can either look at the differential pressure on the filter to see if it's too high. It means there's a lot of dust and dirt accumulated on the filter and needs to be changed. We normally need to do a check on the airflows every 5 years. So we do a measurement on the airflow to see how much airflow is getting into the building. Is it still as per the commissioning stage, the first commissioning that was done? Look at the controls. What is the supply temperature of the fresh air? So you want to have, especially here, properly dehumidified. So normally after the cooling coil, it should be around 12 or 13 degrees C, nothing more than that, especially when it's humid outside. So all these things are parameters that you can look at. Now, for more details, you can look at the operation and maintenance section from the standard. Also, there's another standard from ASHRAE called 180 that looks only into maintenance. So these are two resources you can look at for more detailed recommendations on maintenance.
Thank you. Is it possible to have FCUs with MERV 14 filter?
No, I mean it can, but then the fan would be big enough. It would be almost like an air handling unit. The issue with the MERV 14 is that it has a much higher pressure drop. So if you can find a supplier that can provide MERV 14 with a pressure drop that's okay to be handled by a small fan coil, then yeah, by all means. But in general, you're not going to be able to find that. And also, there was a question about if you can use a DX split. Now, from the standard point of view, you can add an exhaust fan as a ventilation, but in this country with this humidity, you need to have the building or the space positively pressurized. You need to bring in fresh air more than the exhaust. But for residential spaces, for example, you can rely only on exhaust for ventilation. That's allowed, but it's covered in standard 62.2, not 62.1. Just wanted to clarify that.
Perfect. Thank you. Does the glazing have a considerable impact on the selection of appropriate system?
Glazing wouldn't have a lot of effect on the ventilation system or the mechanical ventilation system. But if you're using it for natural ventilation, then obviously the natural ventilation procedure in the standard will basically look into the opening size that you can open. So the glazing means that it's a window that can be opened, and then you can use it for that purpose. But other than that, no, it does not affect the ventilation system.
Thanks. I think we've covered everything now. Thank you all for joining us today. We look forward to seeing you at the Big 5 live in person at the Dubai World Trade Center in September from 12th to 15th. Thanks again, Hassan, for your time.
Thank you,
It was a
Nadi.
great session.
Thanks, everyone.
Goodbye, everyone.
Bye-bye.